Before discussing the extreme value theorem, I want to discuss relative minima, maxima and absolute minima and maxima of functions. This function, which I will call f of x, is defined on the closed interval a, e. At the point b we have what's called a relative maximum of the function. That means that b sits in some open interval. I will call the open interval L. B is an element of L. For all numbers x in this open interval L, f of b is greater than or equal to f of x. Now let's look at the point D. D is also a relative maximum for this function. That means that D is in an open interval which I'll call K, and for all x in the open interval K, the value of the function at D is greater than or equal f of x. As a matter of fact, for this function here, it looks like f of d is strictly greater than f of x, but it could be greater than or equal to f of x for all x in the interval. And similarly for b, it looks like f of b is strictly greater than f of x. But in general, we can leave in the greater than or equal to sign. Now, at the point D, we also have an absolute maximum. That means that f of d is greater than or equal to f of x for all x in the closed interval from a to e. This is the highest point of the function over the entire interval a to e. Now, f of b is only a maximum in a neighbourhood of b. At the point C, we have what is called a relative minimum of this function. M is an open interval such that C is an element of M. For all x in this open interval, f of c is less than or equal to f of x. Actually, from this picture, it looks like that f of c is strictly less than f of x. But in general, f of c has to be less than or equal to f of x. At the point A, we have what's called an absolute minimum of f of x. So that means that f of a is less than or equal to f of x for all x over which the function is defined. For all x an element of the closed interval a to e. Now let's look at what the extreme value theorem says, in particular in relation to this function f of x. If f of x is continuous on the interval a to e, which it is actually in this case, then there are two numbers in the closed interval a to e. Now, the two numbers are actually a and d for this closed interval a and e, but of course one of the numbers doesn't have to be an endpoint of the interval. It just so happens here that one of these two numbers is an endpoint of the interval. One of them is a. Anyway, one of them has to be an absolute min and the other one has to be an absolute max. So that's always true for a continuous function. There are 2 points in the interval, the closed interval over which the function is defined, such that one of them gives an absolute min and the other one gives an absolute max. It just happens in this case that the value that gives the absolute min is the endpoint of the interval a to e. Now, I won't prove this theorem in this video. Here's an example of a function which does not have absolute min and absolute max over a certain interval. The closed interval here is from -1 to +1. It's obvious that this function is not continuous on this interval -1 to +1. It's not continuous at x equals 0. You know, if it's to be continuous at x equals 0, then we want the limit as x tends towards 0 of 1 over x squared to equal 1 over 0 squared. We just plug this number in for x. We just get f of 0. That's the definition of a continuous function. If it's continuous at a certain value, say 0, then this limit must be f of 0, but this is not defined. So f of 0 doesn't even exist. So the function is not continuous at x equals 0. And indeed, there is no value of x that gives an absolute maximum for this function. Well, you might say that at x equals 0 we have an absolute maximum, but actually we don't, because the function never crosses this y-axis. We can get very, very close to 0 and evaluate this function, but we can always find a point that's even closer to 0, such that f of it is greater still. We will never reach a limit. We will never get an absolute max on the interval from -1 to 1. However, we do have an absolute min. At -1 we have an absolute min, and we also have one at +1 actually. So the extreme value theorem doesn't hold here, because for this function f of x equals 1 over x squared, f of x is not continuous. By the way, when we say there are two numbers, one of which gives an absolute min and one of which gives an absolute max, we could have more than two numbers. We could say there are at least two numbers really. Like in this example, even though we don't have an absolute max, we do have two absolute mins at -1 and +1. Here is a function defined on the interval a to b, which has a discontinuity at the point c. Yet on the interval a to b, the function does have an absolute min. It actually occurs at c. And it does have an absolute max. It occurs at b. So in this case, one of the conditions of the extreme value theorem is violated. The function is not continuous, yet everything else holds. Yet there are indeed two numbers that give an absolute max and an absolute min. So obviously the converse of this theorem is false. If we have two numbers in the closed interval a to b, one of which gives an absolute min and the other gives an absolute max, it does not follow that the function is continuous. So we can't reverse this statement. By the way, it's assumed here that f of c is this value here, so we could actually circle this value out. So f of c is equal to this value here.